Welcome, my name is MD Mahmudul Hassan, Assistant Professor at Department of Geoinformation Science at Earth Observation, Patuakhali Science and Technology University, Bangladesh. After this video, you will be able to explain the concepts of Decision Support System, that's mean DSS, and theories, tools and techniques in GIS and RS for urban planning in the context of climate change. Let's begin with a brief explanation. DSS. DSS are commonly used to inform problem solving and assist decision making process by providing tools for combining quantitative data and qualitative knowledge, and for processing this information in order to present, compare, and rank planning alternatives, and ultimately select the one that satisfy the established decision criteria. The DSS, which is built on GIS platform, is useful for a spatial specific assessment of indicators and alternatives. GIS are used to integrate datasets, analyze the various spatial elements, that mean environmental and socio-economic indicators, store the result and visualize them. Special datasets illustrate field observation, provide the key parameters to the available models, and are critical to the DSS in the assessment of planning alternatives. The resulting model output and the assessment result are geographically displayed in the DSS to help the end user to better understand the problem at hand through the visual representation and interpretation of result, and by identifying a spatial pattern and correlations. This approach was adopted in order to inform or support decision making on the basis that the more information provided, the more informed the decision. A geographic information system, GIS, is a computer-based tool for mapping and analyzing geographic phenomena that exist on Earth. GIS provides facilities for data capture, data management, data manipulation and analysis, and also the presentation of results in both graphic and report form, with a particular emphasis upon preserving and utilizing inherent characteristics of spatial data. And it is a widely used tool for spatial urban planning. A GIS has four main functional subsystems. These are: number one, data input subsystems; number two, data storage and retrieval subsystems; number three, data manipulation and analysis subsystems; and number four, data output and display subsystems. Data input subsystems. A data input subsystem allows the user to capture, collect, and transform spatial and thematic data into digital form. The data inputs are usually derived from a combination of hard copy maps, aerial photographs, remotely sensed images, reports, and survey documents. Data storage and retrieval subsystem. The data storage and retrieval subsystem organize the data, spatial and attribute in the form which permit it to be quickly retrieved by the user for analysis and permit rapid and accurate updates to be made to the database. This component usually involves use of database management system for maintaining attribute data. Spatial data is usually encoded and maintained in proprietary format. Data manipulation and analysis subsystem. The data manipulation and analysis subsystem allow the user to define and execute spatial and attribute procedures to generate derived information. The subsystem is commonly thought of as the heart of a GIS and usually distinguishes it from other database information subsystem and computer-aided drafting system. Data output and display subsystem. The data output subsystem allows the user to generate graphic display normally maps and tabular reports representing derived information products. Components of GIS. GIS has 5 components. Number 1, hardware. number 2, software, number 3, data, number 4, people, and number 5, methods. First one, hardware. Hardware is the computer system on which a GIS operates. Today, GIS software runs on a wide range of hardware types, from centralized computer servers to desktop computers used in standalone or networked configurations. Software. GIS software provides the function and tools needed to store, analyze, and display geographic information. Data. The most important components of a GIS is the data. Geographic data and related tabular data can be collected in-house, compiled to custom specifications and requirements, or occasionally purchased from a commercial data provider. A GIS can integrate the spatial data with other existing data resources, often stored in a corporate DBMS. The integration of spatial data, often proprietary to the GIS software, and tabular data stored in a DBMS is a key functionality afforded by GIS. People. GIS technology is limited value without the people who manage the system and develop plan for applying it to real-world problems. GIS users range from technical specialists who design and maintain the system to those who use it in their everyday work. The identification of GIS specialist versus end user is often critical to the proper implementation of GIS technology. Methods. A successful GIS operates according to a well-designed implementation plan and business rules, which are the models and operating practices unique to each organization. GIS Data Model. GIS stores information about the world as a collection of thematic layers which can be linked together by geography. This simple but extremely powerful and versatile concept has proven invaluable for solving many real-world problems, from tracking delivery vehicles to recording details of planning applications to modeling global atmospheric circulation. The thematic layer approach allows us to organize the complexity of the real world into a simple representation to help facilitate our understanding of natural relationships. Vector data format. All spatial data models are approaches for storing the spatial location of geographic feature in a database. Vector storage implies the use of vectors to represent a geographic feature. Vector data is characterized by the use of sequential points or vertices to define a linear segment. Each vertex consists of an x coordinate and a y coordinate. Raster data format. Raster data models incorporate the use of a grid cell data structure, where the geographic area is divided into the cell identified by row and column. This data structure is commonly called raster. While the term raster implies a regular spaced grid, other tessellated data structures do exist in grid-based GIS systems. In particular, the quad tree data structure has found some acceptance as an alternative raster data model. Topology is a mathematical approach that allows us to structure data based on the principles of feature adjacency and feature connectivity. It is in fact the mathematical method used to define spatial relationships. Without a topologic data structure, in a vector-based GIS, most data manipulation and analysis function would not be practical or feasible. Remote sensing, in the simplest word, means acquiring information about an object without touching the object itself. Remote sensing can be defined as the technique recording an object by a device or sensor by measuring portion of reflected or emitted electromagnetic radiation from the Earth's surface. The basic principles involved is that the different objects based on their structural, chemical and physical properties return different amount of energy in different wavelength ranges of the electromagnetic spectrum incident upon it. Most remote sensing programs utilize the sun's energy, which is a predominant source of energy. This radiation travels through the atmosphere and are selectively scattered or absorbed depending upon the composition of the atmosphere and the wavelength involved. These radiations upon reaching the Earth's surface interact with the target objects. That means Earth's surface feature. Everything in nature has its own unique pattern of reflected, emitted and absorbed radiation. A sensor is used to record reflected or emitted energy from the surface. This recorded energy is then transmitted to the user and is processed to form an image, which is then analyzed to extract information about the target. Finally, the information extracted is applied to assist in decision making for solving a particular problem. Stages in remote sensing process. Number 1, energy source. Number 2, energy interaction with the atmosphere. Number 3, interactions of energy with Earth's surface feature. Number 4, recording of energy by the sensor. Number 5, data transmission and processing. Number 6, image processing and analysis. And then number 7, application. Energy source. The first requirement for remote sensing is to have an energy source which illuminates the target of interest. Energy interaction with the atmosphere. The energy on its way from source to target and then from target to the sensor comes in contact and interacts with the atmosphere. Interaction of energy with Earth's surface feature. Different Earth's surface features react differently to the incident energy. Portions of incident energy are reflected, transmitted, or absorbed by the surface. Recording of energy by the sensor. The energy after interacting with the Earth's surface reaches the sensor, which is remote, not in touch with the Earth's surface feature, where it is recorded in a form which can be transmitted to and used by the users. Data transmission and processing. The energy recorded by the sensor is transmitted to a receiving and a processing station, where the data is processed into an image. Image processing and analysis. The processed image is interpreted to extract the information about the Earth's surface feature. Application. The extended information is then utilized to make decisions for solving particular problems. Active remote sensing. Remote sensing system which provides their own source of energy for illumination are known as active sensor. These sensors have the advantage of obtaining data at any time of day or season. Synthetic aperture radar is an example of active sensor. Passive remote sensing. Remote sensing systems which measure this naturally energy are called as passive sensor. This can only take place when the sun is illuminating the earth. Solar energy and radiant heat are examples of passive energy source. Platform. Platform is a stage to mount the camera or sensor to collect information remotely about an object or surface. Platforms for remote sensor may be situated on the ground, on an aircraft or balloon, or on a specific or a spacecraft or satellite outside of the Earth atmosphere. Ground-based sensors are often used to record detailed information about the surface. The path followed by a satellite is referred to as its orbit. Satellites can be categorized as geostationary or near polar based on their orbits and altitude. That means height above Earth's surface. That's all for today. Thank you for watching this video.